welcome back to the last video that we've got in this series for chapter 5 this year anyway. We won't be doing one of the last sections, which is totally fine. But we're going to be taking a look at friction today, which was one of those applications of how we start talking about adding forces at angles. That's actually kind of one of the big reasons why we kind of bring friction and other sorts of motion into this. So we're going to take a look at kind of the idea about what friction is. I know you understand a little bit, but kind of get a little bit more into depth about what friction means or how we start to calculate it. One of our spherical chicken assumptions, right, is that a lot of times we pretend like things like air resistance and friction don't happen in physics problems, and they definitely do. So this gives us a small moment here to be able to kind of peek into the impacts of friction and how important it is in our daily lives. Friction's actually really good stuff, believe it or not. Otherwise, we wouldn't be able to walk anywhere. So talking about friction, we need to think about two different versions of friction. So I'm going to use my lame box here as an example of this. We actually have two different kinds of friction. That's the kinetic and static friction. So what it is, right? It's my phone. We've got two different kinds of friction, and this is going to be something you can try at home yourself. Number one, it has to be a contact force, right? In order to have friction, it's got to be between two different surfaces that are in contact with one another. That's the definition of what it is. It's a shear force or a lateral force. In other words, horizontal kind of thing. We have our two objects, our top and bottom, but yet the friction force is sideways to it. And friction always opposes the direction of motion. So it's kind of a smart force in that sense. If I'm pushing this way and we're trying to move that direction, friction is going to be working the opposite direction. It works in opposition to the direction of motion. Last thing, or last couple things there, you kind of know something about what is involved with friction, what some of the things that are important variables to consider. So one of them is the textures themselves. So I've got a piece of cardboard right here. I have my phone, which has its little rubberized, texture thing on it case. One of the things that those cases do is they actually help to increase friction. They make your phone less slippery. Not only are they impact resistance, but they're drop resistance in a sense as well. So there's something about this texture, this rubbery texture, right, that has something to do with that high friction. If I take something else, like this Post-it note pad, and I put it on the same ramp, it's going to fall right off. So again, it's something about the interaction between surfaces that has something to do with friction. And then the second thing has to do with the weight of the objects, is that if we've got that object there, and if I keep adding more weight to it, my calculator, there's going to be even more friction between it, right? They start to kind of press together and get sticky. So there's something about the weight of the objects involved that has to do with this. Last thing, the idea of static and kinetic friction. Okay, you can actually test this for yourself at home. Get something super heavy and put it on a surface. Like take your physics textbook. You can feel the difference between static and kinetic. Static is the amount of pressure it takes to get something moving. Static means they're holding still. That's what that word means. So if you feel like pushing something heavy, you can kind of tell I'm pushing on it and there's a spot where it kind of pops loose. And you can feel this, especially if you do really heavy objects, where you can feel that pressure on it where it's sort of resisting you before it moves. That's static friction. And then once it's moving, the force it needs to keep it moving at constant velocity, that's kinetic friction. And they're a little bit different in terms of kind of how they react with one another. So with these two things, like I said, give this a shot at home. You can push your couch across the floor, but try pushing on it and feeling that force. You'll feel the object pop as it first breaks loose. The static friction force is always greater than the kinetic friction force. Feel it. Once you get it moving, it will stay moving. But getting it going in the first place takes a little bit harder to get it just like started. So give it a shot and you can kind of feel what it is. So with these two things, we can obviously, I don't say obviously, but we can quantify this stickiness, right? This is called the coefficient of friction. Now, the coefficient of friction is a ratio between two surfaces. So because it's a ratio, it doesn't have any units. We wouldn't say that it's like, grams or something along those lines. It's just a number. So kind of keep that in mind. But we're taking a look at how sticky two things are. And you guys know this, that if I have my phone sliding across cardboard, that's one level of sort of stickiness interaction. If I have the same phone sliding across, say, my desktop, which is that smooth black surface, it would be less of a static friction force, or a kinetic friction force for that matter. So this is the coefficient of friction. Now we use a weird Greek letter for this. You can kind of see it up here. This is the Greek letter mu, is actually the name of that letter. That's why that's funny. But that's a Greek letter. Is the name of this is mu, is the name of that. And it's kind of it looks a little bit like a U, but with a tail on this left side. So it kind of looks like a U like that, but imagine this being a little bit of a straight line to it. When I draw it, I look horrible. I end up kind of drawing it like that. It looks gross. But that's the Greek letter mu, which is what we use to represent the coefficient of friction. Now we use little subscript numbers to indicate whether we're talking about static or kinetic. So if we're talking about the static friction coefficient of friction versus the kinetic coefficient of friction, again, it's a slightly different value. Don't stress about it too much, but just know that those are the little letters that we use to abbreviate the different ones. The next thing is that our formula for actually calculating this ratio, calculating the coefficient of friction, is actually pretty straightforward. It's Fk over Fn, friction. It's actually what this is. So what does these stand for? So Fk and Fn equals mu k. Well, what is Fk? Well, this is the friction force. The K means kinetic. Friction. And again, force. And this one right here, Fn, is the normal force. Well, what the heck are these things? There we go. So kinetic friction force divided by the normal force. So we'll take a look at this on a diagram in terms of what these forces are. Let me go check if it's on the next one or not. Let me know. I'm going to draw it really quick right here. Give me a moment. I'm going to draw it my spot up here. So what are these two particular forces? Come on, pen. There we go. Remember, if we have a surface with a box on it, there it is right there. There's my amazing object, right? We kind of have four forces that are playing in this. Here's number one, which is Fg. Fg, again, is related to is the weight of the object. Remember now, the opposing force to gravity is what we would call normal force. If the object is not moving vertically, then Fg and Fn have the same magnitude, but opposite directions. One's positive and one's negative. So normal force maybe is positive and Fg is negative. Remember, we said earlier that something about friction has to do with the weight of the two objects. Yeah, it is. It's how hard those two objects are sort of pushing up against one another. It's this interaction force between these, Newton's third law, that has to do with what the normal force is. So that's the bottom of that, the weight of the objects. Now, Fk has more to do with the surfaces of the two forces. Remember, we've got, if something is moving, let's say it's moving that direction, right? We would have to have some sort of an applied force. Maybe we're pulling it across the floor, Fa. So if it's moving to the right, we now know which way Ff is, and that's going to be this direction. This would be Ff. And if it's moving versus almost moving, we can call Ff, this friction force, Fk. They mean the same thing, and that's what I want to point out. Ff and Fk are the same thing if it's moving. If it's not moving, we would say Ff is the same thing as Fs, the static friction force. So we can actually write this as Ffs and Ffk if you really want to. Lots of letters. So a lot of times it's abbreviated this way. Fk is the friction force kinetic, or Fs would be the friction force static, whether it's moving or holding still. So again, when we're talking about our friction forces here, this one relates to the stickiness of the two surfaces related to one another. And this one relates to the mass of the object, or the weight of the object. So let's take a look at some values for what this is, just so you have some idea. So here's what some values are. This is a table of coefficients of friction. So you don't need to know these. You're not going to memorize coefficients of friction. That's not the point of this. Coefficients of friction are either given to you, or it's what you're solving for. I just wanted to get an idea of what kind of ranges they are. So take a look. Our coefficients of friction are pretty much always less than 1. Always. Sometimes much less than 1. If you're talking about slippery things like ice on ice right here, they're pretty, small numbers, 0.03. That's a tiny value. 0.003 is synovial joints in humans. That's literally like any sort of movement joint that you've got where you've got fluid lubricated joints like in your knees and your hips and stuff like that. That's a synovial joint. So again, very, very low coefficients of friction. Again, take in mind that the static friction force, this first column, versus the kinetic friction force, the amount of that coefficient of friction is always greater for the static condition than it is for the kinetic condition. In other words, it's harder to get something moving than it is to keep it moving. Once it's sliding, it's easier to keep it sliding. So again, you can take a look just at some ideas of the values. Really, I just wanted you to notice, A, there's no units, right, on any of these, but B, static friction is always greater than kinetic friction, the coefficients, and C, that the values for the coefficients of friction are almost always less than 1. In order for it to be 1 or greater, it's like rubber on concrete, aka tires, right? That's why we use rubber tires for a road. That's why it's so much more slippery when you're talking about hydroplaning your car, if nothing else, right? It's this coefficients of friction so much less. So again, just to give you an idea of what those values are. So let's apply this to a couple of problems, a couple of quick ones here, so you can kind of see what this looks like. So when we're talking about using our free body diagrams to analyze these friction forces, again, this is kind of what I was drawing earlier, that when we have our object and it's moving someplace, let's say it's moving this direction this time. If we have some sort of an applied force to it, if we're pulling it or if we're pushing it, it's fine. FA would be that direction. Just remember that our FF, our friction force, whether it's moving or whether it's holding still and we're not quite moving it yet, would be going the opposite direction. So again, those two are the opposing forces. Second thing is to remember that we've got our upward force and our downward force. Now, these two are almost always in equilibrium for the situations that we're going to do. If we start talking about a situation, we're talking about something on a ramp, then these are not in equilibrium. But for the ones that we're going to do in this chapter, horizontal surfaces, the top and bottom one are always in equilibrium, and those are FG and FN. So when we are doing these, when we're talking about vertical motion, if it's a horizontal surface, FG is equal to FN, other than the sign. Again, one's positive, one's negative, but we can manipulate that however we want to make our math easier. FA and FK is a little bit messier. FA plus FK equals net force. Sometimes they're equal, sometimes they're not. If it's going constant velocity, this is Newton's first law. If they're going constant velocity, then FA and FK are equal and opposite. Okay, positive 10 newtons, negative 10 newtons, just opposite in direction. If it's accelerating, Newton's second law, then these are not equal to one another and we have to add them up. Again, one will be positive and then one will be negative to figure out what our net force is. So again, in the ones that we are going to do in this chapter, we are only going to be dealing with horizontal forces. If we keep going into the last section of the chapter, which we are not going to do this particular, we're talking about forces on a ramp where our vertical and our horizontal forces are not at equilibrium. So we're going to make it easy on ourselves and just deal with horizontal forces. So let's apply it to a problem or two. All right, here we are trying to get a couch moving. You want to move a 105 kilogram couch, sofa, whatever you want to call it. If it takes you 102 newtons to get it moving, what's the coefficient of friction between the sofa and the carpet or the floor or whatever you want to call it, okay? If we're talking about get it moving. So if we're just trying to get it started, we are now talking about FS is kind of what we're doing, static friction. It's not moving and we're accelerating it, we're getting it started. So draw a picture, right? Always draw a picture. There's my couch. It's lovely, isn't it? There's my couch right there. We know some things about this. We know, first of all, FG is this way, and FN is this way. If we're going to move it this direction, this way, we would have to have some sort of an applied force. So our applied force would be like this way if we're pushing it, right? It would be that way, whatever you want to call it. But that means if we're moving this way, that means our friction force is actually the opposite direction, right? Those two are always going to be opposite to one another, almost always. So now we can fill some things in about this to kind of figure out what we've got going on here. We're trying to find the coefficient of friction. So what we really want to know is mu, is what we are calculating for. In this case, we're calculating for mu s. So how do we figure this out? Well, if we're talking about the formula for this, I always remember, okay, I'm going to say a bad word. Mu k equals Fk over Fn. Friction. I'm not saying that very loud because maybe you can think of what I'm saying. But goes there. So if we want to do this, it's the same formula. It's just S's instead of K's. So it's going to be Fs over Fn. So far, so good? Okay. So Fn, we can figure that out. Fs is given to us. Takes 102 newtons to get it moving. We know what Fs is. This is 102 newtons right there. Get it moving. We need to figure out what Fn is, but we can use Fg to figure that out. Fg, remember, we know what that is. M times G. Mass times acceleration due to gravity. Has to do with the weight of the couch. So if the couch is 105 kilograms, and then we know that its gravity is negative 9.81 in the downwards direction, meters per second squared, we can now figure out what Fg is. 105 times 9.81. We get a value of, that sounds like a lot. Fg, it's a heavy couch, 1030.05 newtons. This would be down, right? So if we're trying to figure out what our coefficient of friction is here, we can now know that if Fg is 1030 newtons down, then Fn is going to be equal to 1030 newtons up. They're just opposite directions. So I can call this one positive if I want to. So now to figure out, what do we have? Coefficient of friction, static coefficient of friction, is equal to Fs, 102 newtons, divided by Fn, 1030 newtons. And then all we have to do is divide it. 102 divided by 1030. And we've got 3 sig figs looks like in here. So our static coefficient of friction would be 0.0990. That last digit is significant. So don't forget trailing ones. And there's no units to it. So that is our coefficient of friction. Makes sense that it's less than 1. It's a pretty slippery couch. It's actually not too bad. If we're only taking 102 newtons to get it moving, yeah, we're doing pretty good. That's a pretty slippery floor. So maybe it isn't instead of carpet, maybe it's got those little feet underneath there that make it slide or something like that. I don't know. All right, let's do one more case here where it's a little bit more challenging kind of situation here. So here we have our young girl who's dragging her backpack across the floor. Feels like you going to school, doesn't it? So she's dragging her 18.5 kilogram backpack across the store. She's across the floor, and she's pulling it by one of the straps now. So this is a little bit of a different situation. The strap's at a 24-degree angle. The bag's moving at constant velocity. Okay, constant velocity. And the girl's applying 10 newtons of force. What are the Fn and Fk of this bag? Okay, so let's take a look at it. We've got our backpack like this. We're pulling it at an applied force like that. Here is our ground like this. We have movement. It's going to go this direction. Again, I always kind of do my movement that way just so I know that that's a movement thing. Here's our Fa. What else do we know? Okay, well, we're trying to find Fn and Fk. Okay, coefficient or friction kinetic force. So it's moving, all right? We know that this is 10 newtons. Okay, we know that's a 24-degree angle. That's what that is right there, 24 degrees. And we know how much the bag weighs. Okay, so now we can kind of think about something like this. We know something about Fg, because that's going to equal 18.5, the mass of the bag, right, times negative 9.81. So now we know a couple of other things about this. We know that our friction force is going to be this way. If it's moving that direction, our friction force is this direction. So this is going to be Fk, or Ff, but it's Fk because it's moving. And then we know that our normal force is this way. But we have a little bit of a trick here with normal force, and that's why I use this particular problem. And this is one of those cases where normal force and Fg are not actually quite equal to one another. So here's what we're going to take a look at. We need to look at our x and y components. Sorry, I know you were hoping I wasn't going to go there, but I'm going there. We got to talk about SOHCAHTOA just a tiny bit. Because if we take a look at our forces here, this applied force being at an angle has both an x and a y component to it because it's not flat. I'm going to draw it up here. Here it is. Wow, that's ugly. 10 newtons of force, right? It's at a 24-degree angle. So we have some components here. This is Fa. This is Fay, and this is FAX. So we can figure out what these components are. Now, why do we need to do that? Well, because FAX is the actual component of the applied force that's moving the bag. And now, because this bag is moving at constant velocity, we can now know that FAX and FK are our two horizontal forces that have to be in equilibrium with one another. Okay, the second piece of this vertical force, FAY. So again, we know horizontally, we got FK, and then we've got this direction, FAX. Those are the two forces that are in equilibrium, constant velocity, in equilibrium horizontally. Vertically, we have a couple of different forces that are involved. So vertically, we have three forces. We have a downwards force, FG, and we have two upwards forces. We have the usual one, the normal force, Fn, but we have another upwards force. That is FAY. We have an upwards force here. Now, what this upwards force is doing is actually kind of helping kind of remove some of the normal force. This is the one that everyone misses. These three forces are at equilibrium. How do I know that? The bag isn't moving vertically. Its vertical motion is constant. It's going horizontally. That means the upwards forces and the downwards forces have to be equal and opposite to one another. In other words, the net force here equals 0. So our forces FG, FAY, and FN all add up to 0. Just like here, we would say our net forces in the x direction equals 0. So FAX and FK add up to 0. Sorry, I know it looks a little ugly because I have too many things writing on my page at the same time. My apologies. So FAX and FK, our friction force, have to be equal and opposite to one another. So again, we're looking at these pairs, the X components and the Y components. And because it's moving at constant velocity horizontally and constant velocity vertically, it's 0 vertically, but it's going constant velocity, we know that these net forces have to add up to 0. So let's start filling in the pieces that we've got. So we are trying to figure out FK, that's one of our goals, and FN, that's our other goal. Those are the pieces that we're trying to find. Notice I haven't given you any information about coefficient of friction in here. We could figure it out later, but we don't really need to. So what do we know? Well, we can figure out FAX because we know that FAX and FK are equal and opposite. How do we figure out FAX? SOHCAHTOA. So in this particular case, FAX is the adjacent side. So we're going to use cosine for this. So cosine of 24 is equal to the adjacent side divided by the applied force, the hypotenuse. So cosine of 24 times 10 newtons. Is that what we decided? Yep, 10 newtons of force is equal to 9 point, we got 2 sig figs. Let's call it 2 sig figs. 9.1 newtons. We know that that's FAX. That's this component right here. So we now know that FK is equal to the other direction, negative 9.1 newtons. If FK or FAX, the applied force to the left, is 9.1 newtons, FK, the opposite direction, has to be equal to 9.1 newtons. And again, this would be negative. This version of it here would be 9.1 positive newtons. Okay, again, it's a big leap. I get that. Okay, let's take a look at our vertical components. Okay, vertical components now. Again, I'm looking at this applied force here. Okay, our applied force right here in the middle. This one right here, right? This has got some upwards to it because we're trying to find Fn. So we know that these three forces here all add up to 0. So Fg downwards, we know what that value is. That's an easy one. We can get that quickly. We need to know what Fay is. And again, we can get that from SOHCAHTOA. In this case, Fay, at the top left here of our screen, is sine function. It's the opposite side. So we could say that the sine of 24 degrees is equal to Fay divided by Fa. So the sine of 24 times 10 newtons. Sine of 24 times 10 newtons. I get 4.1 in 2 sig figs, 4.1 newtons. The upwards pull here is 4.1 newtons. It's actually 4.067. You can see my values on there for my last two components. So that means the upwards part here, this one, FAY, upwards, is 4.1 newtons. Our downwards force, 18.5 kilograms times 9.81 is equal to, wow, it's heavy bag, 181.5-ish newtons. Again, it's basically 180 newtons with 2 sig figs. That's our down, 180 newtons, or 181.5, I'm just going to leave it there, newtons is downwards. So now what is the value of our normal force? Okay, the FAY is taking away a little bit of the normal force. Normally, we would say that these two, normal force and FG, are equal and opposite. So if we knew that the downward force was 181.5, then the upward force would be 181.5. But because she's pulling at an angle, she's helping the ground just a little bit. She's removing some of that weight from the ground. I know it sounds funny to say that, but that's literally what she's doing. She's helping. So our normal force is actually reduced just a bit. So 4.1 plus Fn has to be equal to 181.5. Or you can say that all three of them add up to 0, whatever you want to do. The math is exactly the same on there. So if you want to do 0 equals negative 181.5, I'm doing this equation right here, the downwards force, plus the upwards force, 4.1 newtons, plus Fn, which is the other upwards force. It'll be positive. And now we can kind of solve for whatever that is. 181.5 minus 4.1 gives us a difference of 177.385. So if we solve this all out, we get a value of 177.385, 177.4 newtons upwards is equal to Fn. So again, in 2 sig figs, this ends up being 178. It actually ends up being 180 in the upwards. I know that looks basically like the same because she's not lifting it that much, but it is slightly different in terms of the upwards. So our Fk was equal to negative 9.1. Our Fn is now 177 newtons. There we go. Again, they're in opposite directions, and we can figure out the coefficient of friction between those two. So there you go. Once we've got those pieces, kind of understanding these forces at angles and how they sort of apply to one another helps you interpret the different pieces of it. You've got some understanding, a little bit of friction, and a little bit of understanding about how normal force can sometimes change depending on what the upward force is. Same thing with friction force, right? If you're helping a little bit. Hope you liked it. Hope it helped you kind of be even more confused about friction than you were before. Anyway, I will see you guys in class tomorrow. We'll work on some more problems like this. Have a great one, you guys. See you later.